Hi, hello, and welcome to Nami's classroom. Today we are going to see about the 8 great ideas which has been put forward by the computer architects in order to improve the performance of the computer to a great extent. So, what are these 8 great ideas? See, in simple words, we can say that 8 great ideas are the 8 ideas that has been put forward by the computer architects for the design of the computer to increase the performance of the computer to a great extent. So what are these 8 great ideas that we are going to see today? So these are the 8 great ideas that has been put forward by the computer architects. The first one is design of Moore's law. Second one, use abstraction to simplify design. Third one, use the common case fast. Fourth one, performance via parallelism. Fifth one is performance via pipelining. Sixth one is performance via prediction. Seventh one is memory hierarchy. And the eighth one is dependability via redundancy. So these are the 8 great ideas that we have to keep in our mind when we are designing a computer. Because when these things are kept in our mind when designing a computer, definitely the performance of the computer will be extended or will be expanded to a greater extent, because at the end we know that it is a performance of a particular device that speaks the most, because we all are buying some commodity in order to based on the base of some performance. So if the device is not performing well, then we won't recommend it, right? So when you want to buy something, we will first see the performance of the particular device. So in order to improve the performance of a computer, when we are designing the computer, we have to keep all these 8 ideas into consideration. So first we will go with the design of Moore's law. Since Moore's law was put forward by Moore, his full name was Gordon Moore. He is one of the founder of Intel. And what is this Moore's law? Moore's law states that every 18 to 24 months, the size of the transistor is reduced to 30%, and which will lead to increase in transistor count packed inside an integrated circuit. So we know that the first generation computer was made up of vacuum tubes. Second generation computer was made up of transistors, and the third generation computers are made up of ICs. And basically, this IC is a combination of many number of transistors. So he stated that as the size of the transistor is reduced to 30%, okay, for every 18 to 24 months, the transistor size, this is the transistor. Okay, there are different types of transistors are available. So this is the type of transistors, different types of transistors are available, and these transistors, the size of the transistor is reduced for every 18 to 24 months. So what is the use? This transistor, when the size is reduced, you will be able to accommodate more number of transistors in an IC. So this is the picture of an IC. Okay, inside this IC, always remember that all ICs are made up of hundreds, thousands and millions of transistors. So when the size of the transistor is reduced, you will be able to accommodate more number of transistors in a single IC. Okay, that is what he has mentioned. So when more number of transistors are able to be accommodated in a single IC, definitely the performance of the computer can be improved to a greater extent. Okay, so this is what he has stated. That is, every 18 to 24 months, the size of the transistor reduced to 30%. So when the size is reduced, this will lead to increase in the transistor count in an integrated circuit. Integrated circuit is IC. So we have a graph that is input forward by Moore's law, and this is the linear graph, and in the x-axis we will be having time, that means years, and in the y-axis we will be having the transistors, number of transistors. So number of transistors in an IC. Okay, so we can see that as the years increases, the number of transistors inside the IC is also getting increased. And this graph is otherwise known as up and to the right Moore's law graph. We'll go with the second design. Use abstraction to simplify design. So the word abstraction means lowering or hiding the lower level details and giving more importance for the higher level details, that is known as abstraction. So they have given a painting as an example for this. We know that when we start painting, we will be using some pencil sketch first. After that, we may apply some light colors, or we may apply some oil. We may use many different things in the lower layers in order to get the upper layer. At the end, what you will get? You will get a full picture. That is, when the when another person is looking from outside, he can see only the topmost part. He cannot see the hard work that the person has done behind that particular painting. So you may have done lots of things in order to get a final product, but that all lower things that you have done from the initial stage to the stage to get the final output is being hidden, and your final product will be visible by others, so that it will reach the customers in an understandable manner. So that is what we call as abstraction, hiding the lower level details and giving more importance for the upper level details is known as abstraction. So how we will be able to correlate this painting concept to our computer design? See, we know that we are getting laptops. We are buying laptop from shops. We are buying desktops from shops. But we know that we are getting a full-fledged laptop or full-fledged desktop. It is not like we are getting wires and we are getting components and we have to assemble. No, it is not like that. So what they are doing, they are making the work more easier for us in such a way that they assemble all the lower level details in a better way, and we are given the product in a most compactable form. So that is what we called as abstraction. So when you are designing a computer, you have to hide the lower level details and you have to give more importance for the higher level details, and it should be more user friendly to the customers. So there are 5 abstraction levels: hardware, firmware, assembler, operating system, and process. So this is how the abstraction is being carried out. The third one is make the common case fast. See, so here in this case they have given an example as a common case fast as a sports car, or we can simply call it as a car. So consider that there are only 2 passengers and I want to move from Chennai to Vellore. Chennai to Vellore. Okay, so Chennai to Vellore, if I have to travel, it will take around 4 hours or 4 hours. Let's assume that it takes 4 hours. Okay, so when I'm traveling from as we are only as there are only 2 passengers, there is no need to book a van, or there is no need to book a lorry for this particular purpose, because we are only 2 people. So it is it is affordable and it is more comfortable if you are going in a car rather than moving in a very big van. So that is what we call as common case fast. So if we are going in a car, what's the advantage? Advantage is that it will not stuck in traffic very often, because we are traveling in a very small vehicle rather than traveling in a lorry, or traveling in a van which is bigger in size, which may result in more traffic. It may take more time also. So it is always preferred to use the common case first. We have to understand what actually is our situation. In our case, we have only 2 passengers and I want to travel from Chennai to Vellore, and which is more affordable and which is more faster, and definitely selecting a car will be more faster. And now we will correlate this particular concept in our computer design. So consider that we need to do a multiplication. Okay, we know that repeated addition is known as multiplication. Rather than doing the multiplication directly, which is a complex process, we may can do a repeated addition so that the process will be more easier. So that is what we called as common case fast. Consider that we want to multiply 2 into 3. 2 into 3 is 6, we know. But as we are doing as a multiplication, it will be a more complex process. But at the same time, when you are using 2 into 3 in the form of addition, it will be 2 plus 2 plus 2. 2 into 3 means 2 times 3. Right, 2 plus 2 plus 2. So that there also I will be getting 2 plus 2 plus 2 is equal to 6. So in that case, I have to make my computer design in. I have to make the computer design in such a way that it can perform in a better way. That means which is the common case. Which is the common case? That common case I have to identify, and I have to believe that that common case can do the things faster than doing a complex problem. I mean, in our case, multiplication is considered as a complex thing. At the same time, addition is a simpler thing. So, when you are rather than multiplying a particular number, if we add those numbers, because we know that addition is the multiplication is repeated addition. So, if you are adding the numbers to get the multiplication result, then that case will be more common and it will produce the output more faster. That is what we call it as make the common case fast. Next is performance via parallelism. So parallelism is defined as doing multiple number of things at the same time. That is what we call it as parallelism. And for this particular case, they have given the example as a jet engine. So in a plane, there will be multiple number of jet engines available, and these jet engines this just multiple number of jet engines of the plane will perform multiple number of functions at the same time, so that the performance of the jet will be improved to a greater extent. So similarly, how you will correlate this particular jet engine example to your computer design? So we know that if we have multiple number of hardwares available, consider that if the memory is doubled or if the processor is more, if we are having more number of processors, then definitely multiple number of hardware units will help to improve the performance of the computer to a greater extent. And as multiple number of components are present, the operation can also be carried out simultaneously or parallelly at the same time, and this will reduce the execution time of a program to a greater extent. So this parallelism will definitely increase the speed of execution of the program, because we are going to divide the bigger task into smaller tasks, and each task will be provided to multiple number of components, multiple number of units or multiple hardware units. So when multiple hardware units are performing the functions at same time, the execution of the program will be taken in a better way, and it will be executed more easily, or it will take only very less time to execute the instructions. Next is performance via pipelining. So here they have given the example as a pipeline. So what is pipelining? Pipelining is the overlapping of instructions known as pipelining. And in pipelining, we'll be having 5 main stages. One is instruction fetch, instruction decode, then we have execution, fourth one is the memory access, and the fifth one is write back. So these 5 stages will constitute the pipelining stages, and when one instruction is decoding, the other instruction will be fetching. When one instruction is executing, the other instruction will be decoding, and the another instruction will be fetching. So this as it is having 5 different stages, every instruction will be performing each of this stage at a particular time, so that more number of instructions will be executed in a faster way, and hence the execution time can be reduced to a greater extent, and in this way the performance of the computer can be improved to a greater extent. So they have given the example of pipelining in the form of a sequence of pipes. Here you can see that there are many parts of the pipe are available. So consider that the water is getting inside to the pipe in this particular point, and it is flowing over here, and it is flowing out in this particular point. So when the water is flowing out from this particular point, at all these parts, the water will be getting filled at the same time. So it doesn't mean that as the water is going out from this particular point, this will be empty, and once the water is going out, only the water will be coming inside. It's not like that. When the water is going out from this particular outlet, all other parts the water will be getting filled. So it is a simultaneous process. So it is like overlapping of instructions, or overlapping of water will be taken place in each and every sections of the pipe when the water is flowing out from this particular point. So this is what we called as pipelining. So pipelining simply means overlapping of instructions, and there are 5 different stages in pipelining. And more if you are having 5 instructions, then each and every instruction will be performing one particular stage, and so that more number of instructions will be able to execute at the same time. Then last one, sorry, sixth one is going to be performance via prediction. So sometimes we may have to predict in prior whether the branch has to be taken, branch not taken. Some decisions we have to take in prior so that we will be able to execute the program in a better way. For example, they have given this as fortune tellers prediction tool. They have crystal ball is given as the prediction icon. So sometimes we know that if we are not sure of what is going to happen in the future, we may go to a fortune teller and we may ask what is the things that are going to happen in my life. So they may be telling some important things that is going to happen in your life, and based on that we will be doing some puja and some other rituals we will be doing in prior. So similarly in computer architecture also, sometimes we may don't know in the program when we are doing a programming, we may don't know whether the branch has to be taken or branch not taken, we don't know. So sometimes rather than waiting for a long time to judge whether the branch has to be taken or not taken, we can do a prediction. So sometimes the prediction will be correct and sometimes the prediction will be wrong. If the prediction is going to be wrong, it is not going to this misprediction will not be too expensive. So so it is very important that we have to do the prediction when we are rather than waiting for long time. So next is going to be memory hierarchy. So we always know that there are different types of memories available in a computer architecture. In computer, primary memory, secondary memory, you will be having cache memory and all. So there is a hierarchy in which the memories are associated. So based on how it can access the processor. So those memory devices which are very close to the processor or which are very near to the processor will be able to get the data faster, and it can and the access time will be also be very less. But those which are present at the lowermost bottom part of the hierarchy will take more time, and the lowermost bottom part will be having the secondary storage devices, and above that you will be having the main memory, that is primary memory, and above that you will be having the cache memory, and above that near to the processor you will be having the registers. So at first when the processor is given a task of getting particular data from the memory, processor will first search for the data in the register, and after that if the in the register if it is not available, then it will go for the cache memory. If it is not available in the cache memory, it will go for the main memory, and if it is not available in the primary memory or the main memory, it will go to the secondary memory or otherwise known as auxiliary memory. So there is a there is a there is a combination between the three important parameters of memory hierarchy. One is the memory is fast. I mean, the some memory, the size of the memory, then the speed of the memory and the cost of the memory. So speed means how fast it can access the data. So when the processor is giving a task, how fast it can access the data, where is the memory located, so where is the data available. So the speed means how fast it can access the data. Then second one is size. Size means how much will be the storage of that particular device, that memory device. So that is what we call it as size. And the third one is going to be cost. So cost, how much it will cost. So these three are the important parameters when we are considering the memory hierarchy, but it is not possible to achieve all these parameters together in a particular device. So sometimes if the speed is highest, then definitely you have to pay more amount for that particular memory. So sometimes if the speed is very high, if the speed is very high, then it may not be having that much of storage area. So somehow we have to sacrifice any one parameter among these three parameters in order to achieve a single criteria. So that is what we called as memory of hierarchy. So in memory of hierarchy, we usually take three parameters into consideration: speed, size, and cost. So, but it is not possible to achieve all these three parameters for a particular memory. So we have to sacrifice some parameters to achieve other parameters. So this is how the memory hierarchy has been organized. And last one is dependability via redundancy. So dependability via redundancy means if some physical devices fail, the other components of the computer system should be capable of recovering that particular failure, and it has to manage manage to run that particular device. So that is what we call dependability via redundancy. So they have given the example as a truck. So we know that a truck consists of multiple number of tires. So if one tire fails also, other tires will be capable of capable of making the truck move without any difficulty. So that is what we called as dependability via redundancy. So in our computer design, if one component fails, then the other component should be capable of making the system run even though there occurs a failure. So that is what we called as dependability via redundancy. So these are the 8 great ideas that you have to take into consideration when you are designing a computer. So this when we take all these things into consideration, definitely we will be able to design a computer which can provide us with more performance and which can help in executing the multiple number of instructions at the same time. In that way we will be able to improve the performance to a greater extent. So that's all about the 8 great ideas. I hope you enjoyed watching this video. So like, subscribe and share this particular video. And this is Nami's classroom. You can wait for more videos in computer architecture in the future. Thank you.